Let's take a look at the graphs of exponential functions. We'll start by comparing the graph of f of x equals 2 to the x and f of x equals 3 to the x. These are both exponential growth functions because the bases are bigger than 1. To create our graph, let's just make a table of values. I'm going to pick some negative x's, some positive. So let's just plug in the numbers -2, -1, 0, 1, and 2. If I plug -2 in for x, and I'm starting with the function f of x equals 2 to the x, 2 to the -2, we can rewrite that as 1 over 2 squared, or 1/4. 2 to the -1 becomes 1 over 2 to the 1, or a half. 2 to the 0 would be 1. Anything to the 0 is 1. 2 to the 1 is 2, and 2 squared is 4. So now I have a table of values. I'm going to go ahead and plot these points. So on my graph, I plotted x is -2, y is a fourth, x is -1, y is a half. Here's the point 0, 1, 1, 2, and 2, 4. And if I connect the dots, this is the shape I get. This is an increasing function because it is exponential growth. And on the left side of the graph is actually flattening out and approaching y equals 0. Those y values are getting smaller and smaller and smaller, approaching y equals 0. Let's see how the graph of 3 to the x compares. So I'll plug in some x values as well. 3 to the -2 would be 1 over 3 squared, or 1/9. 3 to the -1 is 1 over 3 to the 1, or a third. 3 to the 0 is 1. 3 to the 1 is 3, and 3 squared is 9. And so I'm going to plot those points. So -2, 1/9, -1, a third. And notice we have the same y-intercept. X is 0, y is 1. And then x is 1, y is 3. X is 2, y is 9. That's actually off my graph paper. So 3 to the x, as the base gets bigger, 3 to the x looks a lot like 2 to the x, but the graph is a little bit steeper on the right side and a little bit flatter on the left side. But otherwise, there are some features that these graphs have in common. Both of them are flattening out on this left side, and we can actually call that a horizontal asymptote. They both have a horizontal asymptote of y equals 0 on the left side of the graph. The other thing they have in common is they both have the same y-intercept. They both go through the point 0, 1. Now, let's compare this to a function that is exponential decay, that has a base that is smaller than 1. Let's graph f of x equals 1/2 to the x. Once again, I'll make my table of values. If I plug in -2 for x, 1/2 to the -2, negative exponents mean reciprocal, so I can actually flip that and write that as 2 over 1 squared, or 2 squared, which is 4. And then if x is -1, 1/2 to the -1, well, we can write that as 2 over 1 to the 1, or just 2. 1/2 to the 0 would be 1. Anything to the 0 power is 1. 1/2 to the 1 is a half. And 1/2 squared, 1/2 to 1/2, or 1/2 times 1/2 is 1/4. So if we plot these points, -2, 4, -1, 2, 0, 1, 1/2, and 2, 1/4, we get something that looks really similar to our exponential growth function, except it's decreasing. It's actually reflected over the y-axis. But we do see some similar features, and I'm actually going to summarize all of our features of our basic exponential function, f of x equals b to the x. So again, if we have exponential growth, if that base is bigger than 1, our function is going to be increasing. And if we have exponential decay, our function is going to be decreasing. But regardless of which case we have, we are going to have a horizontal asymptote of y equals 0. If it's exponential growth, the asymptote is on the left side of the graph, Exponential decay, the asymptote is on the right side of the graph. Both of these functions have the same domain and range. The domain is all real numbers. The arrows go to the left forever and for the right and to the right forever. You can plug in any number you want for x. But the range is all positive numbers, everything from 0 to infinity. We can see that in the graph. The outputs, the y values, are always bigger than 0. And that's not including that 0. The graph never actually approaches y, or never reaches y equals 0. Neither of these graphs have an x-intercept. Again, we have that asymptote at y equals 0. They're never crossing that x-axis. And both of these graphs, regardless of the base, have the same y-intercept. The y-intercept is at 0, 1. That's because if you plug in 0 for your exponent, you always get an answer of 1. And then finally, if that base is bigger than 1, we have exponential growth. The function will be increasing. If that base is smaller than 1, but bigger than 0, we have exponential decay, and the function will be decreasing. Now we can graph other exponential functions using the concept of graphing transformations. So for example, if I want to sketch the graph of f of x equals 2 to the x minus 1 plus 3, I can start with the parent function y equals 2 to the x. That's what we graphed earlier. Y equals 2 to the x is going to have a y-intercept at 1, and it's going to go through the point 1, 2, and we'll see that horizontal asymptote of y equals 0 on the left. If I want to graph f of x equals 2 to the x minus 1 plus 3, this plus 3, notice that's outside of the exponent, outside of the exponential function. That is an output transformation. It's going to impact y values, and we're going to be shifting the graph up 3 units. So the plus 3 is going to move the entire graph up 3 units. The minus 1 is inside the exponent, so input transformation impacts the x values. We do the opposite of what it says minus 1. So we're actually going to add 1 to all of our x values, and that's going to take our graph and shift it to the right 1 unit. So I have tried to draw that. I moved my asymptote up 3 units. So when I shift everything up 3 units, that moves the asymptote up to y equals 3. And then I took my point. So here's my y-intercept. It was at the point 0, 1. I moved it up 1, 2, 3 units, and then to the right 1 unit. And I did the same thing with a couple other points. For example, I had the point 1, 2. I moved that up 1, 2, 3 units, to the right 1 unit. And then you can see on the left, we've now got an asymptote of y equals 3. Let's look at another example. Same process, different example. Sketch the graph of f of x equals negative 2 to the x minus 1. Once again, I'm going to start with the same parent function. Y equals 2 to the x has a y-intercept of 1, goes through the point 1, 2, and has that horizontal asymptote of y equals 0. The negative in front of the 2 to the x, it's outside of the exponent, output transformation, that impacts my y values. That's going to take all of my y values and actually make them negative, and that's going to take the graph and reflect it over the x-axis. So I've tried to draw that in red here. I took my y-intercept at 1, and I reflected it to negative 1. So now I have a y-intercept at negative 1. The point 1, 2, when reflected, became 1, negative 2. And then you can see that asymptote was also reflected over the x-axis. The asymptote is still at y equals 0, but now it's been reflected over. It's on the other side of the x-axis. Then we have this minus 1. That's another output transformation. That is going to shift the graph down 1 unit. So I took my reflected graph in red, and I brought everything down 1 unit. That brought my asymptote down to y equals negative 1. And then my y-intercept, I brought that down 1 unit. And I took the other points I had plotted and brought them all down 1 unit. And there in purple is my final answer. that would be the graph of this transformed function. So one thing I'd like to point out in these examples is notice that the vertical shift is determining where that asymptote is. It's at y equals 0 for our parent function, but if we move the graph up or down, that moves the location of that asymptote. So let's see if we can answer some questions without actually creating a detailed graph. I have the function 4 times 1/2 to the x minus 2. To find the y-intercept, if I don't want to take the time to make a graph, I can always find a y-intercept by just plugging 0 in for x. And so I'm going to go ahead and do that. I'm going to plug in 0 for x, and that gives me 4 times 1/2 to the 0 minus 2. 1/2 to the 0 is going to become 1. So we've got 4 times 1, which is 4, minus 2, and that equals 2. So my y-intercept here is going to be located at the point 0, 2. Now to find my asymptote, I'm going to think about the graph. I'm not going to do a very precise drawing, but I'm going to think about what's happening to this graph. So the 1/2 to the x means we have exponential decay. But the important thing when it comes to the asymptote is this minus 2 right here that I've circled tells us that the graph has been shifted down 2. And so if we shift that graph down 2, that's going to move our asymptote to y equals negative 2. Again, that vertical shift, that constant, is going to tell you what your asymptote is. So y equals negative 2 is my asymptote. And then to find the domain and range, I am going to think about what my picture looks like. The domain, and this will be true for all of our exponential functions, is all real numbers. I can see on the graph the arrow goes to the right forever, it goes to the left forever. But the domain of exponential functions should always be all real numbers. They don't have any square roots or fractions or things that give us those undefined values. So my domain is all real numbers, and then the range is always going to be connected to that asymptote. So my range would be starting at negative 2, not including negative 2, again because that was my asymptote, and then up to infinity. So range is negative 2 to infinity. All right, that was my last example. I hope this video was helpful. Please let me know if anything is unclear.